and being interested in my project. I'm very excited to be here. And just some background about me. I'm from the University of Pretoria, and I form part of the Clean Energy Research Group. So my personal interests are in heat and mass transfer, as well as energy storage. In my presentation today, I will discuss the following. Starting off with my introduction, which will just be a reason for my project, as well as some background important information. Then I go into my experimentation, which will be my reason behind all of this, and construction and how I conducted my experiments. Then I dive into the results, which is going to be an analysis of just all the data that I collected. And then next will be my simulation, where I will talk about the setup that I used, the software I used, and my results. And then I will do just a quick brief overview of the uses of this technology. And then finally, I will summarize everything in a conclusion. The field of energy storage is particularly beneficial in South Africa today, due to the current energy crisis that we're all facing. This adversity calls for new ways to innovate and use energy more wisely. My research project this year was specifically in the area of thermal energy storage, which can best be described as a way of storing heat for later use. Think of it like charging and discharging a battery, except instead of storing electrical energy, we're storing thermal energy. This can be especially useful in situations where the demand for heat varies over time, and you want to use the heat even when the source isn't actively producing it. For example, in a solar energy system, you might collect heat from the sun during the day and store it for use at night when the sun is not available. This way you can have a continuous supply of heat energy. In order for thermal energy to be effective, the implementation of load shift dynamics is crucial. This refers to the variation of energy usage depending on demand on the grid at that time. In figure 1 here is an example of this. This graph is from Eskom. It's from March. That's what was available when I got it. And you can see here that there are some extreme highs and extreme lows. This is very problematic when it comes to energy production because a finite amount of energy can be produced at a time. And this up and down, obviously, as we're experiencing now with load shedding, in these extreme up times, the supply cannot keep up. So as a strategy to get a more stable graph, the use of thermal energy with load shift dynamics can be implemented. This way, you can charge your thermal battery during times of low demand, so the bottom parts of the graph, and discharge this energy during peak demand, the top. This will result in a graph that does not have these extreme highs and lows and will rather be a more level graph, which is beneficial in many ways. A common form of thermal energy storage is a hot water accumulator. This works essentially as a smart geyser, which heats up water during low demand periods and discharges it during high demand periods. Accumulators are commonly used as they are energy efficient. However, there has been minimal utilization in industry of enhancement through the incorporation of phase change materials. Phase change materials, also commonly known as PCMs, are substances which have a very unique property. They release or absorb large amounts of energy when they change phase, essentially acting as a thermal battery. My project aims to enhance an accumulator and quantify the impact that phase change material has in order to create a more efficient thermal battery. My research begins with investigating different types of phase change materials. I decided to use paraffin wax as it is relatively cheap, available, and has very good energy storage capabilities. The exact paraffin wax which I used was the Sasol M3B wax, which has a melting point of 58 degrees Celsius. This melting point is perfect considering that my working temperature for the accumulator is 70 degrees Celsius. This temperature is higher than the melting point of the wax, therefore there will be melting, and I can use the properties of phase change material. It is vital that the wax and water do not mix. Thus, I chose to encapsulate the wax in copper pipes, which I sealed with copper end caps. In order to quantify the effect of the wax, I decided to have 3 different cases for testing and comparison. Across the cases, I kept the exposed surface area of the copper tubes at 2,543 centimeters squared, but varied the amount of wax per case. This was done, as you can see here in figure 4. Case 1 had 15 millimeter tubes. Case 2, I used 28 millimeter tubes, and for case 3, I used 54 millimeter tubes. These different diameters, enabled me to vary the amount of wax per case without changing the exposed surface area of the copper. It can be seen in this table that the percentage of wax in each case varies greatly, with case 1 having 3.1%, case 2 having 5.6%, and case 3 having 10.6%. These large discrepancies were vital in determining the effect of paraffin wax and the energy output. So just to explain what I've shown in this table here, these were my 3 cases. So for my first case was the smallest pipes that I used, which were 15 millimeters. And as you can see here, the number of pipes also varies. So as it's 4 for case 3, 10 for case 2, and 17 for case 1. This was so that I could keep the surface area constant between those 3 cases, and also vary the amount of wax. This volume fraction of wax is the amount of wax per case divided by the total amount of water, so total volume. After the experimental setup was designed, construction and assembly could begin. I started off by prepping my tank. I made use of a 25-liter mild steel vessel, and I created an inlet and outlet, as can be seen here in figure 5. After that was done, the tank was insulated, as I showed here in figure 6, to ensure minimal heat loss during experimentation. In order to seal the vessel, I made a base from silicone-treated chipboard and a lid from acrylic to ensure that I could see into the tank during experimentation. The lid and base are held together by rods and nuts, as can be seen in figure 7. So the way that I would hold this together is the rods would go through the drilled holes, and then I have nuts on the top and the bottom that I would tighten to ensure that the vessel is completely sealed. In order to hold my pipe arrangement in place, I used a plastic netting that can be seen in figure 8. This was to act as a horizontal spacer so that my pipes did not move during testing as water was flowing through it. Due to the fact that I was using phase change materials, it is important to be able to monitor when the phase change occurs. For that reason, I included a single clear acrylic tube, as I've shown in figure 9. You can see it here, just in the middle there. That's the paraffin wax. In order to monitor the melting process during testing. In order to quantify the effect of the paraffin wax, I did the experiment in 2 phases. For each case, 2 phases for each case. First, it was the charging cycle, which is then immediately followed by the discharging cycle. The charging cycle begins with the tank filled with water at 20 degrees Celsius, as can be seen in figure 11, the top row. The wax can be seen to be completely white and solid at the beginning of the charging cycle, which is what you're seeing inside those acrylic tubes. The water preheater is switched on, enabling an inlet temperature to the vessel of 70 degrees Celsius. Heated water continues to run through the tank until the wax is completely melted and all temperature fluctuations stop. The fully melted wax can be seen in figure 11, the bottom row. Here you can see the opaque color, and according to the specifications of the wax, that's when it is fully melted. So it's not a clear wax when melted. When we see that, then the discharging cycle can begin. The preheater is switched off, allowing 20-degree water to flow through the vessel. This cool water continues to flow until the wax solidifies again and all temperature fluctuations stop. After testing was completed, it was time to process all of the data that I collected. It should be noted that the total number of thermocouples per tube varied per case. This was due to restrictions in the lab setup that I was using. Figure 12 shows the number of thermocouples and positions per case. So case 1, which was my 15 millimeter tubes, only had 1. Case 2 had 2 thermocouples which were positioned evenly spaced. And case 3 also has 3 thermocouples and they're evenly spaced. One of the first observations to be made when I was analyzing the data is the significant temperature gradient which forms across the length of the copper tubes, as can be seen in cases 2 and 3. From these 2 cases, you can see that the bottom thermocouple and the top thermocouple were at extremely different temperatures at the same time. This gradient is as a result of the wax slowly solidifying, and as the wax solidifies, its density will increase, meaning that it will sink to the bottom of the tubes. The warmer wax will float to the top and be the last part to solidify. The next results are the most important from this experiment. Figure 16 represents the heat transfer rate across all 3 cases during the discharging cycle. The heat transfer rate represents the amount of energy that is transferred from the wax to the water. This is an indicator of the effectiveness from each case. It can be seen in figure 16 and 17 that there is not a large difference between the 3 cases, despite the large difference in the amount of wax per case. Case 1, shown in gray in figure 17, is above the rest on the energy transfer graph. This indicates that that was the orientation that worked the best, despite having the least amount of wax. In order to verify results from experimentation, I decided to do a simulation of case 3. With the use of ANSYS software, in order to observe and better understand what was happening within these tubes. The first part of a successful simulation is the mesh. Meshing in ANSYS is essentially creating a grid of small pieces to accurately simulate and analyze the behavior of complex systems, like this one. The smaller the grid is, the more accurate the results are. My mesh can be seen here in figures 18 and 19. In order to get a mostly consistent mesh, I broke up my area into the regions that you can see here in the different colors. So these different colors are not different materials. So these bigger blocks are one material, but I broke it up for meshing, and the same with these tubes. So the square and these regions around it, it's just the phase change material, but I broke it up in order to get a more consistent mesh. It should be noted that only the wax, copper, and water was simulated in this model. It was decided to do this for the ease of calculations, as it will take less time to run the simulation. The model here is made to be adiabatic, meaning that there is no heat loss in the system. This assumption is valid, as due to the insulation that was put on the tank, the heat loss is expected to be minimal. The simulation was done in 2 phases, charging and discharging. First is the charging cycle, which can be seen here in figure 20. All materials begin at 20 degrees Celsius with a vessel inlet temperature of 70 degrees Celsius. This simulation is run until all of the temperatures reach the 70 degrees Celsius and all of the wax has completely melted. On this slide, figure 21 shows the temperature profiles as the simulation progresses. And figure 22 shows the liquid fraction. The liquid fraction is a useful profile as it shows how much of the wax is solid or liquid at this phase. The red areas are fully liquid. So as you can see in this cross section, the red over here would represent the water, and the red inside these tubes is the paraffin wax. From these figures, it was observed that melting begins at the bottom of the tubes. This was expected as the inlet of warm water was positioned at the bottom. Next is the discharging cycle, which is the opposite of the charging cycle. All components in the vessel begin at 70 degrees Celsius with an inlet temperature of 20 degrees Celsius. I have chosen to only show the liquid fraction here as it is the most interesting and relevant. As can be seen in this short video, the wax within the tubes slowly solidifies from the surface of the tubes inwards. This solidification process creates a solid wax barrier around the inside of the copper pipes, as can be seen here. You can see the blue slowly moves in. The problem with this phenomenon is that paraffin wax has a very low thermal conductivity, and this inhibits it from effectively being able to transfer energy through the material.